This is the Earth Science Classroom. Welcome back to the channel. This video is a review video looking at Unit 1 and Unit 2 topics, concentrating on things like Earth spheres and what is Earth science. Let's check it out. So this video is looking at 5 major topics to discuss, and the purpose of this video is to review the information on these topics for any large assessment or test. And you can use this for general studying or information, or just to get ready for a upcoming test or assessment on these topics. So the 5 units or topics discussed is what is Earth science as a general introduction, the scientific principles that scientists use to gather information and come to conclusions and analysis and to figure out how things work, especially in Earth science, and then look at the Earth as a very large system, how it works, how it functions, and the different components of that system, and then looking at topographic maps, which is part of mapping and cartography, and looking at how we map and gauge and scientifically understand the Earth's surface using contour lines, which are a type of ISO line, and then looking at the mapping part, which is the grid system of the Earth using latitude and longitude to locate things on the Earth geographically, and to look at how the two different types of grids, latitude and longitude, how they function and their main terms. So what is Earth science? Now, Earth science in the US is an area of study looking at how the Earth functions, its processes, both physical, chemical, biological processes that contribute to the Earth functioning. Now, in other parts of the world, like Europe or Australia, it could be called geography or physical geography or geoscience, but generally it's the science of everything else besides biology, pretty much, where the biological processes are just in biology in terms of ecology, and it can also relate to environmental science, but pretty much Earth science is the physical, chemical processes that govern how the Earth functions. Now, we can bring in chemistry and physics and engineering into this as well, but the core is how the Earth functions. So there are certain disciplines that go into Earth science, topics like meteorology, which is how the atmosphere works, hydrology, which is how the oceans and water works, oceanography, which is more on the oceans itself than just the general water, and looking at things like geology, which is a very large, all-encompassing subject, looking at all the solid rock components of the Earth, and they can split off into topics like geomorphology or limnology, which is the lakes and rivers, looking at geologic time and how the Earth has changed over its 4.3 billion years. And a cool part of Earth science curriculum in the States is it includes astronomy, which is a beautifully amazing topic by itself, but it's included in Earth science. So the areas of study, so if you meet someone like out and about and you ask them what to do for a living, you can say accountant or lawyer or businessman or a construction worker. So the areas of study that people might do in Earth science if they get a Earth science education would be a thing like a geologist or a meteorologist. So people that study the various components of the atmosphere, or the Earth as a geologist, or an oceanographer, or a astronomer who studies space and stars and concepts in and around our Earth in space, basically. So as an introduction to Earth science and this assessment is, we're looking at the scientific method, which is how scientists come up with these ideas, theories, laws, analysis and conclusions based on natural phenomena that happen on the Earth. So the scientific method is a process of how to think through and work through problems or a hypothesis or an idea that they have or someone has about, basically curiosity. So how things work. How does that work? How does this work? How does that function? And it was basically perfected or created this method, this step-by-step method of acquiring information scientifically through various famous inventors, astronomers, and thinkers of the 16th and 17th and 18th century. People like Galileo, Brahe, Kepler, Newton, Einstein. They all worked on this certain way, this method of acquiring the information they want in a step-by-step, methodical, reasoned, scientific way, which we now know as the scientific method. And it's 5 to 7 steps based on what you look at, and it has this flow of a question or hypothesis. You acquire data, you experiment, and then you analyze the data received from the experiment or acquired, and then from the analysis you make conclusions, and then either you can work back and redo and tinker what you have, but you are using a step-by-step method that is consistent throughout science that would allow you to come up with a method that is repeatable, and you could show other people around the world and they could redo the experiments in the same way and hopefully get the same outcome. So that links into what is called a hypothesis, which is a question or an idea about what's going on, and you'll try and prove it or disprove it using this scientific method. And the outcome could be a theory. So this happens because of the experiment. This phenomena occurs, but not everyone agrees with it. So a theory is where it happens, but not every scientist is in agreement. But then a scientific law is where everyone agrees that the outcome is correct, it is concrete, like gravity. Whereas a theory would be like the Big Bang Theory, which is still up in the air of what actually happened 13.6 billion years ago. And then we can get into the ideas of how these scientists worked through the method, which is the observations. It's what you see, what you perceive with your five senses. Inferences are what kind of statements you make based on the observations. It's more like what you think based on observations. Observations are more your facts. Okay? And then accuracy and precision. Accuracy is you are aiming for a target, you're aiming for a goal objective. Do you hit that target, yes or no? Precision is hitting the same results or getting the same results multiple times. So you're not always accurate, but precision means that you're having the same outcome multiple times in a row, repeating that same thing. So let's say if you are an archery athlete and you are trying to hit a target, let's say you miss a target 5 times, exact same place, that's precision. You're not accurate, but you are precise. Then we have the scientific variables. Variables are things that can change within an experiment, in this case. So as you do an experiment, there's 2 types. There's independent and dependent. The independent starts with an I. I equals I change. I can change things in the experiment, and I can adapt the experiment to what I want based on how I want the experiment to go. So I can change anything. And then the dependent variable is the data or the numbers or whatever facts you want to get out and acquire from the experiment. So it's the purpose of the experiment. So if I'm going to time someone running 100 meters, the time of that athlete running 100 meters, that'll be my dependent variable. That's what I write down in my data sheet. How fast was this person? And then the independent variable, what I could change is what time of day do they run? Do they run in sneakers or trainers or running shoes? Do they run in bare feet? Do they run backwards, forwards? Do they skip? Do they hop? Do they do it when it's raining or when it's dry? Do they do it when they're wearing a big winter coat or a t-shirt and shorts? So the independent variable can change, but the dependent variable is what you take out, what you measure. Then we got something called feedback and equilibrium. So feedback is not in terms of like support, but in terms of the cause and effect within a system. And this can be talked about more in a system, but we're going to look at how things change and the effect of change, and equilibrium is that balance that a system acquires. So that leads us on to what is a system. A system is a machine or something that works with multiple components that work together to allow the system to function in different ways. You could have small systems and very large systems. You could say the largest system would be the universe. Then the types of systems. We have open, closed, and isolated. Now this is based on energy and matter. Energy that can go in and out of a system, and matter again can go in and out. Now within the system, energy and matter can move around and play a role and function within the system. So the open system, that's where energy and matter can just flow in and out freely. A closed system is where you have matter that can't leave. It's stuck in, energy can move and come in and come out, but matter is stuck inside. And isolated means that both energy and matter are inside the system, and there is no interaction or transference or interchangeable nature where energy and matter can leave that system. They're trapped in the system. So isolated systems are very rare in the in nature, and the Earth itself is an open system because we send and receive matter from space to the planet, and we also send and receive energy. So we give energy off through things like albedo and black body radiation, and we receive the energy obviously from our sun, right, the EM spectrum. So then we get what is the Earth system. It's a combination of all these different components of the Earth that work together to function to create our living planet. And the Earth's spheres are the different components that make up the Earth's system. Things like the atmosphere, the biosphere, the hydrosphere, the cryosphere, and the geosphere. So all these 5 major parts of the Earth. Cryosphere is the water component that's frozen, so ice and sleet and snow, so ice caps and north and south poles and snow-capped mountains and perhaps permafrost. And the hydrosphere is all the liquid water, okay, on the Earth's surface, both oceans and on terrestrial land like rivers and lakes and streams and underground water. The atmosphere is all the gaseous layers, so the layers of the atmosphere. The biosphere is all living organisms, so all the biota, all the flora and fauna. And the geosphere is all the solid rock components, so the Earth's layers, the interior, the core, the mantle, the crust, the different layers of soil and rocks and rock cycle and volcanoes and all that awesome stuff. They all combine to create our living world. So how do they connect? So in terms of connections, you're looking at, let's say, the geosphere, which is the solid rock. So take volcanoes and magma and lava, which is the molten or liquid part of rocks. Then we look at the atmosphere. So when a volcano erupts and spews out its tephra, its ash, its pyroclastic rock parts like pumice and tuff, the lava comes out and flows on the surface, which forms basalt or andesite. That is going to interact with the atmosphere, with the gases. So there's an exchange of gases with like water vapor and CO2 and SO2 and NO2 within from the volcano to the atmosphere. So that's an example of a connection. Or let's say the biosphere and the hydrosphere. So the living component of the species of animals and the water. So you talk about how animals and fish and certain mammals live in the oceans and how water allows the biosphere to survive through drinking water like humans. So all these connections are either very obvious or some are not so obvious, but they're always happening and occurring. So then we get to topographic maps. Now this is part where we analyze the Earth's surface, how we take a 2-dimensional image or picture of the Earth from an aerial view, a bird's eye view looking down on the Earth, and how do we use information, geographic information, using these lines on the map to indicate the elevation. Now elevation is the height above sea level. Now in this case we're looking at the terrestrial or land masses, so above sea level. We do have it below sea level as well, but in this case we're looking only above sea level. So sea level is generally at 0 feet or 0 meters. We can use feet or meters for the unit of measurement. So these contour lines are a type of isoline. Basically it's a line that connects equal elevation on the Earth's surface. So if you're standing at an elevation 10 and you walk to another area that's elevation 10, then a new area that's elevation 10, you can connect those points of reference on the map with a line that means that anywhere along that line would be a contour line. So, or 10 feet. So these lines on these 2 maps, these are all contour lines. They are connected with a smooth, no right angles, no straight lines, smooth line that connects areas of equal elevation on the Earth's surface. And these can tell you a lot about the environment without actually being there. So it's kind of like a remote sensing. You are understanding the area without actually being there. So these contour lines can tell you information like the elevation. Like here we have 4,000 or 4,200, or over here we have 800. We can tell how the landscape is, how the terrain is based on if it's hilly or gentle or valley or a slope or a mountain range based on the contour lines. So the first thing we can do is look at the contour interval. The contour interval is based on how the elevation changes between each contour line. And not every line would have an elevation. So the ones that have elevation listed are the thicker ones, and these are called the index contour lines. So for example, this one right here, the 4000 right here, that's an index contour line. It's a bit thicker, more pronounced than the rest, and you can see it. So with the index contour line, it's every 5 contour lines on a map is an index line. So we can use this. So let's say this is you're staying here on elevation 4000. 1 contour line, 2 contour lines, 3, 4, and then 5. And again, you have this 4,200. So you have this difference of 4,000 to 4,200. There's 5 contour lines. So you subtract 4,200 from 4,000, so that's left with 200. 200 divided by 5 is 40. So what they're saying is that even without the elevation being listed on this contour line, we can now figure out the elevation of this line and therefore the elevation in between the lines. So wherever you're standing, you can figure out the elevation. So this is 4,000 and the contour interval is 40. That means that between the contour line, the elevation will go up by 40 or down by 40. So we know this going this direction is going up towards 4,200, a higher elevation. So we know that this line here must be a increase by 40. So it's 4,040, this contour line. This one's 4,080, 4,120, 4,160, plus 40 is 4,200. So you can put it into the map and check that the contour interval is correct, and it works. So the index is every 5, has the elevation, and you can figure out the contour interval based on this with a little bit of simple math. So you take the difference and divide by how many lines there are, which is 5, always 5. So then we can look at gradient. Gradient is awesome because you can see how steep an area. So gradient means the angle of the slope. The slope is how inclined or declined the landscape is. So how steep is that hill, or how steep is the decline or drop on that hill. Now, because the contour interval is the same across the whole map, that it's 40 in this case, and in the top right map it's 20, that the contour interval is consistent, we know that if the contour lines are close together, like this in parallel lines, which they usually are, that indicates that it's a very steep gradient. The hills are very steep because it changes by 40 feet over a very short distance. So you're going down very steeply by 40 feet quickly over a short distance. That's what the contour lines indicate if they're close together. If they're far apart, like over here, that's more of a gentle slope, a more flatter surface. And then the other rules are the contour lines can't cross over because you can't have the same location have 2 elevations. That's impossible. Okay? Any spot on the Earth's surface has only 1 elevation. And they must be connected in a full loop. There must be a place where that same elevation continues and it will join up in a loop. Maybe it's off the map, you can't see it, but it will join, like here, a nice complete loop. Whereas the other contour lines would complete the loop off the map. So we'll start with latitude. I always start with latitude as the basis. So latitude and longitude, that's the mapping or grid system, how we use to locate places around the Earth, Earth being a sphere, being a 3-dimensional circle, an oblate spheroid, being it's fatter around the equator as it is taller from north to south. So latitude is to do with north and south, the North Pole and South Pole, and the equator. So the equator is 0, the North and South Pole. The Arctic and Antarctic are 90 degrees north and south. Then we have the Tropic of Cancer and Capricorn. Cancer is in the north, Capricorn is in the south, and these are at latitudes 23.5 degrees north and 23.5 degrees south. Then we have the Arctic Circle, which is 66.6 degrees north, and the Antarctic Circle in the southern hemisphere, which is 66.5 degrees south. Now, I mentioned hemispheres. Hemisphere, hemi means half, sphere means the ball. So half the ball. So the equator splits the Earth into northern hemisphere and southern hemisphere. Then we're looking at the mid-latitudes, the tropics, and the polar regions. The tropics are in between the the Tropic of Cancer and Capricorn, so around the equator. And then the mid-latitudes are between generally 30 to 60 degrees north and south. And also the polar regions are generally above the Arctic Circle to the North Pole and the Antarctic Circle towards the South Pole. So these areas divide the Earth into three main sections, and it's all based on the solar insolation, the concentration of sunlight that we receive, and also to do with the tilt of the Earth, which is 23.5 degrees, which fluctuates over time, and to do with seasons, how the Earth is going to orbit and revolve around the sun, and based on the tilt, it's going to change the angle of the sunlight, the angle of which, and the areas of which are exposed to more or less sunlight, which gives us our winter and our summer. And in the mid-latitudes, we get our spring and fall. So if you're around the equator and the extreme high latitudes of the North and South Pole, you don't really get 4 seasons. You get in 1 or 2 seasons based on your latitude. So if you're in Aruba, for example, in the Caribbean or Caribbean, you don't get a winter. You're just going to get pretty much consistent heat all year round and some nice off-the-shore breezes. And if you're in the Arctic Circle or Antarctic in a research base, you're not getting really a summer. It doesn't really get very warm down there, and you don't really get any kind of seasons besides harsh winters and crazy storms. So latitude plays a big part in the climate, solar insolation. Then longitude. Longitude is east and west, from 0 to 180 degrees west to 180 degrees east. Now it starts on the prime meridian, which goes through Greenwich, London, which is in England, my home country, and it designates the east versus west hemispheres. So from London going towards Europe, going towards Asia, that is the eastern hemisphere, and from England going west towards North America and South America, that is the western hemisphere. So the longitude lines, so latitude lines are called parallels. The longitude lines, they're called meridians. They are slices, like slices in an orange. And the slices go from North Pole to South Pole, and they go up and down, but the measurements, the degrees, go from east to west, compared to the latitude, where degrees go from north to south. So these lines of slices, or these meridians, the prime meridian being the first or main meridian that goes through London, that's 0 degrees, okay, and then the other side, which is 180 east or west, that's on the other side of the Earth, and that's called the anti-meridian. Now we use longitude mainly for time. So as the Earth spins on its axis, gives us night and day, we look at time zones and how the sun hits the Earth at certain areas to give daytime, and the Earth spins and turns. That same area that was in the sunshine is now away from the sun, because the Earth is a sphere, and that experiences nighttime. So the 24-hour spin of the Earth on the axis is going to look at longitude in more detail and time zones. So when does the sun rise, when does the sun set, and how we calculate different times in different areas of the world based on those different times of sunrise and sun setting. So like right now I'm in the United States, but it's Wednesday morning, but in the other side of the Earth, in New Zealand or Fiji, it is Thursday. It's Thursday already. So different parts of the world have different times, and these times are split into time zones based on degrees of longitude. So if you take a full circle, which is 360 degrees, and you take how many hours in a day, which is 24, and divide that, you get 15. So every 15 degrees you go east and west, you're basically changing the day by 1 hour. So if you start in London on GMT time, which is 0 degrees longitude, and go 15 degrees to the east, so you're in Europe, then you're going to be an hour ahead. So anything east would be to add hours. So an hour. So if it's say 12 noon in London, then anything that's 15 degrees east in Europe will be around 1 p.m. in the afternoon. Or let's say you travel west towards the United States and you fly to New York from London. That's usually going to be a 5 or 6 hour, maybe 7 hour flight. And you're going to change your location by so many degrees. So let's say 70 degrees west. So you just take 70 divided by 15, which is 4.6, let's say 4.5. So you'll be roughly 4.5 hours behind London, Why is it behind or ahead based on the direction east versus west? Because the sun is going to rise in the east and set in the west. So the west is still moving towards the sun and the east is going past the sun. Okay, so it's a certain direction that is consistent. So going east from London, you're going to add hours to your clock, and then going west, going to the Western Hemisphere from London, you're going to subtract or minus hours from your clock. Then if you travel around further enough to 180 west or 180 east, you get to what's called the international date line, which is where the day changes. So if you're going to go west or east over the Pacific Ocean, where this line is located, you will travel from Tuesday to Wednesday, or from Wednesday to Thursday, depends on which direction you fly or move to based on the line. And so it's kind of an awesome thing, but a terrible thing for people that are traveling to keep changing their clocks by a whole 12 to 18 to 24 hours based on where you are.